In this video, I will be discussing a number theory problem. Suppose that integers x, y, z satisfy x minus y times y minus z times z minus x equal to x plus y plus z. Prove that x plus y plus z is divisible by 27. So, the product of x minus y minus z times z minus x is equal to x plus y plus z. So, the question is going to be the same thing as proving that this product is divisible by 27. So now, you can let the product equal to p. Okay, so now, first of all, since the question is asking by 27 divisibility, well, we know that 27 can be broken down into 3 times 3 times 3. So, we will actually now want to just prove that 3 is a factor of x minus y, 3 is a factor of y minus z, 3 is a factor of z minus x. So 3 of these factors have contained factors of 3. So then that means that x plus y plus z will have a factor of 27. And then, well, to tackle with x minus y, y minus z, and z minus x, it's going to be challenging. But we can tackle it using x, y, and z. Because if 3 is a factor of x, 3 is a factor of y, then obviously 3 is a factor of x minus y. For example, if 3 is a factor of 6, 3 is a factor of 3, then 3 is a factor of 6 minus 3. The more professional way of showing this will be called Congruence Modulo. It's basically the same thing showing remainders. So, if x congruent to y modular 3, then this means that x minus y will be congruent to 0 mod 3. Using this knowledge, we can then get that using x, y, and z, we can prove the divisibility by 3. But then, once again, we are faced with different scenarios. If the remainders are all distinct, 0, 1, and 2, or the remainders are going to be all different. I mean, at least 2 of the remainders are congruent. So let the first case begin. All remainders are distinct. Mod 3. So this means that the remainders can be 0, 1, and 2. So we can get that x plus y plus z congruent to 0 plus 1 plus 2. This will be congruent to 0 because 3 is congruent to 0 mod 3. But then you get that x minus y, y minus z, z minus x. 3 is not a factor of this because these remainders, so you see if x has a remainder of 0, y has a remainder of 1, z has a remainder of 2, x minus y will have a remainder of negative 1, y minus z has a remainder of negative 1, z minus x has a remainder of 2, and then the remainder total will be 2. And so that won't be a multiple of 3. Contradiction, because these are supposed to be equal. So now go to the second case. at least 2 of x, y, z have congruent remainder. Mod 3. Now, without loss of generality, any scenario will work, but assume x congruent to y mod 3. Then, using this, we can get that x minus y congruent to 0 mod 3. So then you can get that since x minus y is a factor of p, so 3 is going to be a factor of p. Wait, it's going to be mod 3. Okay. So then this will mean that three is going to be a factor of x plus y plus z. Or in other words, x plus y plus z will be congruent to 0 mod 3. And now you can replace y with x. This is because y and x are congruent to mod 3. So after replacing x and y with x, the result will still have a remainder of 0 when divided by 3, and it's still going to be a multiple of 3. So then, we can then get that 2x plus z. Now here's the tricky part. This can be formed into, well, 2x plus z minus 3x will still be a multiple of 3, because minus 3x is also a multiple of 3. So 3 is going to be a factor of negative x plus z. So this means that z and x from here, if you want z minus x to have a 0 mod 3, then x must be congruent to y. X congruent to z mod 3. So then you will get that x congruent y congruent z mod 3. So then you'll get that 3 is a factor of x minus y. 3 is a factor of y minus z. 3 is a factor of z minus x. From these, you can get that 27 will be a factor of x minus y, y minus z, z minus x, because, as I said before, these three all provide a factor of 3. So 3 times 3 equals 3 times 3 times 3 will equal to 27. So then you'll get that 27 will be a factor of x plus y plus z. And the proof is complete. The key concept of this problem is that you have to know that you can break down 27 into this. And then you have to know this identity. While I didn't prove it in a rigorous manner, you can do some examples to prove it. Then you can split into cases, because in remainders, you always have to think of the cases where remainders are distinct or when remainders are congruent. And then you can manage to prove that there's a contradiction when it's distinct. And it's congruent, we can manage to prove that through algebraic manipulation, x congruent, y congruent, z mod 3. Then we got our final answer. Thank you for watching.